So now we're going to leave the exponent problems that we spent a few days on, and we're going to jump to the opposite of an exponent, which is the radical. And radicals refer to square roots, cubed roots, fourth roots, so on and so on. We're going to stick with square roots today. Tomorrow we'll get into some of the higher level roots. But to begin with, we just need to review the definition of a square root. A square root is the operation that is asking a question. What number multiplies by itself to give you the value under the square root? Hopefully we're all familiar with that definition. Now it's important we understand that most square roots are not going to work out to whole number answers. We've talked before, and you've learned in previous classes about perfect squares, where if you have the square root of 25, obviously that's 5. That's something you should be very familiar with. But most of our square roots are not going to be rational answers. They're not going to work out to whole numbers. We're going to have things like the square root of 37. And the square root of 37, if you type that into your calculator, is going to give you a big long decimal. And that's only part of the answer because it's actually an irrational number. It'll go on forever. So therefore, rather than trying to round this or write out a big long decimal, we're going to simplify radicals. We're going to rewrite them in a simpler form, just like you simplify fractions. And this is something that most of you have done before, and so we're going to go through one method quickly, and then I'm going to show you another way that I like to do these. Our first method we're going to look at is the perfect square method. And that's where if you have a problem like the square root of 20. When you look at that, most of you look at 20 and you can see the factors of 20. And what we're looking for is we're looking for a perfect square that goes into 20. And in this case, the largest perfect square is 4. So we rewrite the square root of 20 as the square root of 4 times the square root of 5. And then we say we can simplify the square root of 4 down to 2. So we get an answer of 2 times the square root of 5. That's called simplified radical form, when you end up with this 2 times the square root of 5. This method's a great method when you have numbers like 20, because most everyone can look at 20 and say 4 is a perfect square and 4 goes into 20. Now when we're working with these smaller numbers, that works well, but sometimes we're going to get into larger numbers and it might not be as easy to figure out what perfect square goes into it. So I have another method that I like to use that, again, you are welcome to do either method, whatever is more comfortable for you. But this other method is one that I've found it works all the time, and it helps those of us who don't have a great number sense and know what numbers go into something. It makes it a little bit easier. And that's called the factor tree method. So if you look here, I have the square root of 20. We're doing the same problem. And I break 20 down into 2 times 10, and then I can break 10 down into 2 times 5. That's called a prime factorization or a factor tree. You've done those way back in 4th grade, and so again, we're connecting to something that you're comfortable with. And so what that allows me to do is rewrite the square root of 20 as the ends of the branches on my factor tree, as the square root of 2 times 2 times 5. And that brings us to our definition of a square root. We said a square root, we're looking for what number times itself. So therefore, in this case, if you look at our prime factorization, I have a 2 times a 2. That's a number times itself. So therefore, that comes out in front of the square root, because that represents the square root of 2 times 2, which is 2. So really what the factor tree method says is we're looking for pairs of numbers, because when you're under a square root, a pair comes out and goes in front of the square root. So therefore we have this pair of 2's here, and those 2's come out to make 1 2 in front, and the reason why that happens is because the square root of 2 times 2 is 2. So that's called the factor tree method. Let's look at a larger number where the factor tree method is going to really help. So we have this situation here where we have 5 times the square root of 216. Most of us can't look at a number like 216 and say, oh, I know the largest perfect square that goes into that. So our first method, our perfect square method, is a little more difficult on this one. And this is where most people find the factor tree method to be easier. So I've gone ahead and done a factor tree on 216. Like I said, a lot of people can't tell what the largest perfect square that goes into it is, but they know 2 goes into it because it's an even number. So I just take my calculator and I do 216 divided by 2, which is 2 times 108. Now, I know 108 is 9 times 12. You might have used 2 and 54 to get to 108. It doesn't matter. Either way, you'll get to the same answer at the end of our factor tree. So I broke 108 into 9 and 12. 9 is 3 times 3. 12 is 4 times 3. And 4 is 2 times 2. So now I have the ends of my branches here. I have 2 3s, 2 2s, another 3, and another 2. So therefore, I have 3 3s and 2 2s. And you notice in the, 3 3s and 3 2s. And you notice in the original problem there was a 5 in front. So I kept that 5 in front. And now, what I'm looking for, again, is numbers times itself. So when we look in here, I have a 2 times 2 under a square root. So therefore, that comes outside and makes this 2 out front. Same thing with my 3's. I have a pair of 3's, and the square root definition is a number times itself. So this 3 times 3 moves out and becomes this 3 in front. Now this 2 and this 3 don't have anything to pair with, so therefore they can't leave the square root. They stay inside. So we have on the outside 5 times 2 times 3, which is 30, and the inside, which is 6. Now let's quickly look at how I would do this in a real time-limited situation where if I'm doing my homework and I want to do this problem, here's how I would go about doing this. I might not write out this whole bottom section here. If I were doing this, all I would do is say, I'm doing a square root, so I'm looking for numbers times themselves. So when I look at my square root of 216, my factor tree here, all I'm going to do is say I have a pair of 3's and a pair of 2's. I have a lonely 3 and a lonely 2. The pairs come outside and become 1. I have a 2 and I have a 3. And I have on the inside, I still have a 2, and I still have a 3. And so that represents my pair of 2's, my pair of 3's, my lonely 2 and my lonely 3, which gets me to my answer of 6 radical 6. You don't necessarily have to write out the prime factorization like you see at the bottom. This is how most of you would do this problem. So our final part here is what happens if we mix variables into this. And so if we mix variables under a radical, or you would have the square root of x to the 5th, we're going to do the exact same thing we did with our factor tree. We're looking for pairs. So if I write x to the 5th out, I can make a pair of x's, and then I can make another pair of x's over here. So I have 2 pairs of x's. That means 2 x's can come out of the square root. So therefore we have x times x, which is x squared out front. I still have this leftover x that does not have a pair, so therefore it's left on the inside. So I'm left with an answer of x squared times the square root of x. So your homework today will be simplifying radicals. Please make sure you take the time to write down any questions you may have. We'll talk about this at the beginning of class tomorrow.